this colloquium with Diego Frustaglia from the University of Seville. So we start our session with an invited talk from Ivan Vera Maroon from University of Manchester. So Ivan will talk about perspective on topology and geometry for nanoelectronics. As a general rule, for people that have questions during the talk, please post on the chat. At the end of the talk, you can also unmute yourself and speak up if you have any question for Ivan. Please, Ivan. Yeah, Ivan, you just to unmute yourself, please.
Yes, that would be useful indeed.
Yeah, please, Ivan.
So, good morning, everybody. Thank you, Carmine and Diego and the rest of the amazing group behind this great effort of continuing with meeting and discussing and learning about each other's work, even in the face of a pandemic. That's greatly appreciated, and I very much an honor to have the opportunity to share with you this first presentation of today's mini-colloquium. So my name is Ivan, and I was tasked by the organizers to start with an sort of overview or perspective on how we use geometry, or how we could use geometry for nanoelectronics, and in particular for spintronics. So what follows is sort of a personal take of how current areas, in particular related to 2D materials, but also related to more common materials, relate to combining geometry and topology to explore spintronics. So it's certainly not exhaustive, and let me start by my apologies for all the amazing work and people that I might not reference during the presentation. All right, so before getting to the subject matter, I always like to start with at least one slide of motivation. And it's not only for the beauty of the physics and the fundamentals behind these areas, but really for the potential impact that it could have in the near future. And I'm really convinced that we're talking about the near future, because as much as I love graphing and the amazing subject of 2D materials, I believe that the greatest area or subject that has the record from going from Nobel Prize winning fundamental research to multi-billion-dollar industry is spintronics, no doubt whatsoever. And one of the exponents is that represents this record is certainly how going from the study of fundamental pure spin transport and later other non-charge-based degrees of freedom has developed into a full-flag inclusion in the international technology roadmap for semiconductors, where a big chunk of all these technologies, in particular, those that are present in the top right quarter, using non-charge based transport and using novel mechanisms and materials, are really composed in large part by spintronic related concepts. And I am convinced that what the spintronics managed to do, from the humble beginnings of GMR to the multi-billion industry of magnetic recording, could probably be replicated in the next decades, but now in the area of spin logic. Now, if we want to work towards that goal, besides the fundamentals of spin transport and topology, we have to keep in mind that we are dealing with a completely different architecture where we try to not only use regions of devices where charge current is present, but we try to decouple that charge current from other degrees of freedom, be it spin or more generally valley, entropy, etc. And this is in part what this talk aims for. So what we're going to cover is essentially 4 brief parts. First, we're going to start looking at geometry at the smallest possible scale, at the curvature of single atoms or few atoms, and then discuss briefly how that was explored initially in graphene, and the open questions that are still almost a decade ago in the area of atomic scale-induced spin orbit effects into the materials. Then, in a second brief fact, we're going to look at a bit larger scale, going from the atomic scale to the scale of a large bunch of atoms, where we now are not looking at the intrinsic lattice structures of the bare materials, but we look at the superlattices involved on the fabrication of heterostructures based on these 2D materials. And then we are going to go in a transition where we look at a slightly larger scale that could be from few nanometers to even larger, where we now really talk about the geometry of the device, and we aim, and I will give you just a few examples of great advances in the last couple of years that have really moved forward the field of going from the amazing theoretical works that many of you have worked on to actual experimental realizations of these ideas. And then as a closing bit, we're gonna now go back down to earth and move away from these amazing 2D materials, and then take a first step into applying these concepts of curvature and geometry for spintronics in the more mundane but directly applicable, technologically applicable area of metallic spintronics. So that's the whole idea. Please feel free to interrupt me with questions, and I hope the chairman will give me a heads up when a question pops up. Okay, so that's it. So here we go. So if we start with the first step of looking at curvature at the smallest scale, at the atomic scale, and then we question how does this curvature or these atomic deformations, right, lattice deformations, affect the spin transport in graphene and in general other 2D materials. And the first hurdle we find is that the actual mechanism that currently dominates spin transport in these materials is still heavily under debate. We can take 2 approaches. One, where we assume that these materials are completely clean, and then we are in a limit where the limitation for spin transport, and in particular for devices that exploit pure spin currents, are only driven by the intrinsic spin orbit effects in that material, plus whatever device architecture enhanced effects we can apply, like, for example, Rush electric field from substrate interfaces, or by applying an actual potential using gate electrodes. But in reality, what most people in the field agree is that we are at least in some sense limited by spin orbit effects that are present in what we call the dirty limit, where we have impurities, unintended impurities that are resulting from the fabrication processes, and on which we don't have a direct control on, nor we have an explicit way to make them visible and to quantify it at the level of the final device. So even if we use Raman, AFM, etc., it's really hard to pinpoint the origin of the present spin orbit relaxation. And it is within this context that we operate in the area of spintronics into the materials, and of course in the de facto standard material, which is graphene, which is really the only one that serves as a proper spin channel because of its long spin relaxation length. So having said that, if we start from the more intrinsic aspect, then we have the seminal work that were maybe, I don't know if anyone is present, or any one of these authors, but at least the one that I know personally is Paco Vinea, where they really developed this concept of how curving a layer of graphene increases the spin-orbit coupling because of the mixing of the orbitals in the carbon atoms. And therefore, you could associate the degree of curvature of a structure to the degree of a spin-orbit coupling. And that's certainly the case for a carbon nanotube, for a C60, but it is also the case for a ripple in the graphene lattice. Now, if we go to what would be the extreme case of just taking a single atom and pulling it out of the lattice slightly out of plane, then we have really that area of atomic scale curvature. And it was not really until recently, and by recently I mean within the last decade, that people looked at it theoretically with first principle methods that try to go beyond mean field approaches, and where in particular one of the groups working on that would be the group of Jaroslav Fabian in Regensburg, where they came out with very good numbers, realistic numbers for the spin orbit coupling associated with what experimentally would be realized via adding hydrogen atoms on the graphene lattice. And then you could see that the curvature would indeed induce the spin orbit coupling on an atomic scale, basically a few atoms on the order of a couple of atoms around the defect. And this is something that many people in the field started to explore. Among those, my colleagues and I, in my former lab in the University of Groningen, in the group of Barban base, we explore the result of this functionalization of graphene using hydrogen, and realize that the Fermi level dependence of the relaxation rates were actually in agreement with the modeling performed by Jaroslav Fabian and his team. And this is something that Jaro framed within the context of impurity-induced spin-orbit coupling plus localized magnetic moments in a graphene lattice, and that therefore we could relate the increase in relaxation, the decrease in relaxation rate at high Fermi energy, at a sort of disordered, convoluted energy dependence of what would be the intrinsic dependence of the relaxation rate that they extracted as a sort of a spin split structure with a maximum relaxation rate at a finite Fermi energy. This is the case because that data that they used there was the data from our earlier work. And indeed, it kind of got the field started into looking at the role of these defects at the atomic scale, and in particular to control fabrication processes to limit the impurities. And this is where curvature at the first of the scales that I mentioned plays an essential role. Now, I would never forgive myself if I present that and I am in a conference, at least virtually in Spain, and I don't make the clarification that that is just one part of the story. The reality is that the theoretical understanding and the consensus for the relaxation mechanism in graphene is not there yet. And one completely different approach that has been championed by Stefan Roche and his team in ICN2 in Spain is that of coming up with highly scalable, efficient methods to probe spin transport due to intrinsic spin orbit coupling in graphene. And what they have come up is with is in a picture where even without atomic scale defects, strong localized magnetic moments and so on, they can reproduce this dependence in energy, dependence on energy of the relaxation rate, just by including as ingredients the the spin orbit coupling in graphene, plus the presence of electron hole photons, which you would have anyway in a perfectly flat graphene when you have charge impurities around, right? And this is really an important consideration because it really changed the discussion in the last couple of years about how to improve the quality of the devices to identify this source of impurity. So this is where I make my first quick stop, and I make a short announcement that you are very welcome to look for the presentations of Jesus Toscano and Noel Natera tomorrow in this conference, where they will be presenting some of the work that is ongoing in Manchester, where we now keep this work going on and now going beyond the general functionalization with, let's say, hydrogen globally in the flake, where now we can control this sort of local scale curvature defects or SP3 defects instead of using impurities that you cannot control spatially. Now what we use is a laser-aided method to include molecular moieties in the graphene that play a similar role in terms of charge and spin transport. So that's just the advertisement number one. Now, if we go on considering how we exploit these spin orbit coupling effects, then of course, in terms of devices and generating pure spin currents, the primary candidate is to use the enhanced spin orbit coupling to create a large spin Hall effect. And this is what about now almost 7 years, the group of Barbarosos Yilmaz in NUS, they were pioneers because they demonstrated in a non-local configuration that you could get a large degree of non-locality by introducing this atomic scale curvature in the form of hydrogenated graphene. So again, this is where we hit a bottleneck a couple of years later, because we thought that things were clear and that would be just the way to do spintronics in graphene. And then the group of Barban based in Groningen applied the same method, got similar large non-locality, but with further tests applying magnetic fields and looking for spin precession in the response, they concluded that whatever the source of that non-locality, it was not a spin transport. So this is where we are in the area of atomic scale defects and really confirming that we can create on-demand pure spin currents. The answer is that this thing is under debate and work is still going on, which doesn't sound so exciting, but I can take you now to the next scale, which in my opinion is even more exciting, which is when you go from the atomic scale to that one of the scale of a superlattice. And why do I mention this slide? Because that is really for me one of the very interesting next steps in the area of spintronics using 2D materials that directly combine concepts of topology and actual geometry of the lattice, both in terms of deformations and actual geometry that, as we will see in the next few slides, but that in the field so far has been absent, which is kind of amazing when you realize that we are already a good few 8 years since the first demonstration of graphene pure spin transport on top of a atomically flat hexagonal boron nitride substrate. And since then, since the work of Paul Sommer, work after work has been coming on, in part led by the group of Urban Base, in part led by the group of Roland Kawakami in the US, where we now have high quality graphene devices fully encapsulated with HBN. We have finally seen electrical field control due to electrostatic gates and rush by spin orbit coupling. But we are still to see the active use of that superlattice structure for graphene spintronic devices. And to me, that's really, an amazing consideration, because we are now quite so many years in which these two fields have coexisted side to side, but they have not really now go to the crunch time of putting them together and trying to exploit them. So what sort of effects can we, in our perspective, identify for exploiting moire patterns or superlattices for spintronics in graphene and 2D materials? Well, first of all, of course, is that of generating the superlattice and the corresponding electronic reconstruction that can be easily identified as the generation of secondary neutrality points, both for holes and electrons, that have clear signatures in terms of regular magnetotransport data, like the Hall signal, but that now we should try to incorporate this into spintronic devices where we probe these features and their effect on pure spin current. This is work that is actually going on at the lab. And again, this is the second point where I make a brief advertisement. And I say that those interested on how these superlattices can be exploited for thermoelectrics, please join the presentation of Christopher Anderson, which is now the last advertisement I promise I do during this presentation. So if we now try to link that area of moire superlattices to the topic of our discussion, of course, then the first step is to realize that when we align these structures, now we can achieve a commensurate to incommensurate transition, where we end up with areas that nicely are commensurate to each other and form domains, but now separated by these walls or sort of solitons in 1D lingo, like for the case of the Frenkel contour of a model, where we know that we have now a different degree of strain and geometric distortion of the lattice, going from the atomic to the superlattice scale, so from atomic to few nanometers. And this is something that and now I give credit to people that deserve it. An amazing student, now postdoc in Manchester, worked on a couple of years ago, where we fabricated these structures and now look at detailed STM and AFM data in the different regions in the superlattice, and then by quantifying the lattice constant, then one could identify very clearly that you would have a deformation locally of the graphene lattice just because of this alignment. And that was a work that in Manchester at least was led by Colin Woods, who is now a PDRA in our group. So if we now try to exploit this for spin or any sort of non-local transport, then of course the first candidate is that one of generating a non-locality in a purely non-local transport configuration, where again we have a current path, a voltage detection path, and we should be able to detect a large degree of non-locality, usually in the primary neutrality point. But now, because of the superlattice structure, we can also exploit that non-charge-based degree of freedom also on the secondary points. And for this, graphene on HVN is a nice candidate because the thing just works. But of course, it's not very tunable. So now this takes me to the second person I want to give credit for this second part of the talk, which is a colleague of ours, Dennis Van During, that had worked on introducing this electrostatic gating of the non-charge-based transport in bilayer systems. And why bilayer? Well, first of all, because you can now tune the bandgap, and therefore you have full electrostatic control of those hotspots for the Berry curvature, where we can see in this 2D map that by playing with both top and back electrostatic gates, we can now control independently the charge density and the displacement field. And as we increase the displacement field along this diagonal, we create a gap in the system, evidenced here by the local transport, but we simultaneously also enhance the amount of conversion from charge to this non-charge based degree of freedom, in this case valley, and therefore achieve a very large non-locality, which in this case can be of the same order of magnitude as the local response itself. So in terms of spintronics, this would be really the way to go as a next step to look at the role of the superlattices and topological effects for spin and valley non-charge based transport. Now, this is what Dennis did in our group, but now I go to my third point, which is that transition from the small scales of the superlattice to a larger scale, where we now deal with actual geometry, deformation, and curvature of the graphene. And there is no place where to start, certainly at least on the experimental side, than to cite the seminal work on the graphene bubbles, where these accidental concoctions of graphene strain, deform due to trapping impurities and so on the substrate, can really create a pseudo-magnetic field so large as in the hundreds of Teslas, and therefore create pseudo-Landau levels that are easily visible in spectroscopy. Now, this is certainly, at least in my opinion, the first experimental demonstration of using actual geometry to for the purpose of topology in these materials, and that you can provide transport. But of course, for the purpose of an actual device, it's not really that useful, because this is just a localized curvature. You can put some big leads here and there, but you cannot really probe it unless you come with the tip of an STM and write at the exact place. So this is where we now go to the ideas of trying to make this larger scale curvature globally available in a device in order to give observable experimental signatures in the experiment. And here I just would like to highlight two such examples. One of those, the initial work of Cresty, together with Paco, Castro, and Stefan, where they realized that in many of the suspended graphene structures, you actually have a naturally occurring stretching and rolling over of these 2D materials. So in principle, it could be realizable to probe the effect of the rolled up geometry of this graphene layer or any other 2D material that acts as a thin and but flexible sheet, and therefore applying a strong magnetic fields and obtain a strong magnetoresistive responses, just because of the combination of the Hall effect and the quantum Hall effect in this material, plus the winding of the actual layer. Now, this particular design has not been really demonstrated experimentally, but what is interesting to see is that the features predicted there, which were in the high quality or ballistic or quantum Hall regime, are actually more generally visible, even if you go to the diffusive regime, which makes it really hopeful for us experimentalists that this can be realized. And this is where then I highlight the work by Carmine and company, where you realize that, okay, if you manage to create this rolled up geometry, even if you don't go to huge fields or go in the quantum Hall regime, you actually can create visible signatures in terms of magnetoresistance, and therefore create a sort of artificial AMR in a material that intrinsically could have zero spin-orbit coupling. And to me, then this is really one of the promising areas where we can now try to play these tricks on 2D materials. And what, in my opinion, is one of the recent first steps along that direction, not as fine as actually rolling over the individual graphene sheet, but if you look very carefully, then you can definitely identify bends on graphene flakes that might give you direct access to such a fold that if now you are smart in assembling the device, you can indeed create a structure where you can exploit this combination of geometry in terms of this folded 2D material, plus the introduction of electrostatic gating, in this case, in order to modulate the band gap in a folded graphene bilayer, such that you can create two gapped regions after the fold of that bilayer flake, but then in the transition, you are bound to have these states originating of topological origin because of the opposite pseudomagnetic field in the two valleys in the bilayer graphene, which now, as per this demonstration of last year, allows you to achieve a topological transport along that fold in a system that otherwise is difficult to control.
Ivan, sorry to interrupt. If you
Yes.
could conclude in 5 minutes, then we have some time for questions.
That's perfect, because then this is the last slide before I go to my last 5 minutes of the talk, which is that it's only this year where we now have seen the possibility to exploit these structures, not at the local level of a single bubble or at the difficulty of trying to roll up a graphene layer, but actually with the capability to use strain engineering, or sometimes, happy accidents in the fabrications of these devices, in order to use a standard thin film mechanics to generate beautiful arrays of such bucklings in monolayer graphene, which now create a large area, two-dimensional array with large enough pseudomagnetic fields that can lead to these pseudo-Landau levels percolating throughout the whole sample. And this, of course, is not just great in terms of ultimately combining topology and curvature into these systems for device applications, right, for using them in actual transport devices. But of course, this connects with the more recent and broad topic of flat bands in these Moiré systems, of which I have zero time to cover, of course, but then again, I make a little advertisement for the corresponding mini-colloquia in this conference. And this takes me then to my last 5 minutes of the talk, which is to say, okay, so where are we at the moment? So we know that there have been these initial works at the very small scale into the systems. There is now progress at the intermediate scale of superlattices, but so far no direct applications to spintronic devices. So where can we go in terms of actually going for applications that combine geometry and spintronics? And this is where it really pays off to look at adjacent fields, in particular that of nanomagnetism, which people like Stuart Parkin, with the concept of the racetrack memory, really spearheaded to look in the third dimension and at curved nanowires with to moving magnetic domain walls and so on. And more recently, the amount of work into making actual nanostructures that are curved and understanding the corresponding magnetic ordering has been really a very active field of research. in particular led by Denis Makarov. So the question is, well, can we at least use some of these learnings from the field of magnetism to create functional curved devices for pure spin transport, right, for actual spintronics? And this is where, until 2-3 years ago, we were really limited that all standard spintronic devices, even those that are in principle easy to fabricate using simple metals, were perfectly flat. So the goal here was to really look beyond those flat devices and go from something that looks like this, a flat thin film, to something that potentially could look like that. Basically, a fully bended 3D structures where we can probe spin transport in a non-magnetic channel, for example. And this is then the last thing I want to comment on, which is the work that was published last year, where in collaboration with a bunch of great people that I will mention at the end, we managed to fabricate for the first time such curved spin transport channels to probe directly pure spin current. And even in a simple material like aluminum, you are bound to find surprises when you start to play with the geometry. So the first goal was how to make these structures, and then that was kind of an easy first decision. We say, okay, we'll start with what we can do at the moment. Let's just not try to make this channel grow curved by some sort of magic trick or buckling and so on, because that's really tricky. Let's actually do an approach that is more bottom-up. Let's structure the substrate so that it can act as a template to create channels that we can design at will in terms of their geometry. And for that, we use standard silicon oxide, focus on matching, and managed to achieve a very nice control of the geometric features of such trenches. Once you have the trench and you have the channel, now you have to, of course, create the channel, understand what role does the geometry play. And something that was very evident only after we did some experiments at fault with these structures is that making these non-homogeneous channels where the geometry and the deposition technique, which in this case was evaporation, creates these local scale variations of the thickness and the corresponding properties, actually opens up an avenue to control in separate ways the transport of charge and the transport of spin. And an easy way in which we can realize that is that as you make the material thinner and thinner, the resistivity at some point starts to be dominated by surface scattering, and therefore the actual sheet resistance of the structure shoots up quite rapidly because of the decrease of the thickness and the increase of the resistivity. Whereas on the other hand, a key figure controlling spin transport, which is the spin relaxation length, in these metallic systems is inversely proportional to the resistivity. And therefore, the way that this spin relaxation length increases goes only with that resistivity, and it's on a slower rate than what happens with the actual sheet resistance. So now we can see that at least there is a possibility to optimize the thickness on a small scale in order to control how these two figures increase and how both of them affect the corresponding charge and spin transports in different ways. And this is basically what we try to show with this toy concept that I don't want to spend too much time now. But this is the key idea. So just cut into the chase to finalize the presentation. Then we managed to create such curved nanochannels based on standard metals. And something we directly saw is that as you would introduce this trench here, you would see that the pure spin transport response, represented by this spin valve signal, starts to decrease, 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 until eventually it dies out, whereas the actual charge resistance through the channel then starts to increase. And this opposite response, at least to first order, we can understand as the result of the resistance of the channel increasing because of the longer length and thinner regions. But then at the moment of trying to understand the actual trend and model it, which is what these lines show, we actually failed initially because there was no proper model to apply to such inhomogeneous channels. And this is what brings me to the actual understanding of this work, which was the contribution from my colleagues, and in particular, Carmine Ortiz, where we modeled the geometry of the channel in a consistent way to include both the length of the channel, but also the varying thickness or inhomogeneity in the structure, taking into account that that would lead to an increase of the resistivity, and calibrated all those parameters in the model using this set of different devices going from the flat to the curved regime. And we managed to achieve a very good agreement with the data. And this is what ultimately led us to understand that to model the spin transport data, you really have to bring into the picture that the relaxation along the channel is non-homogeneous, and to introduce the right mechanism for this relaxation, which in the case of these standard metals is one where the relaxation length is inversely proportional to the resistivity, as I mentioned, which is an Elliott-Jaffet spin relaxation mechanism. And only then we had the ingredients to model this, and still not actual easy model, which is what Carmine then also developed, extending the well-known Takahashi-Maekawa model for a non-local spin transport. So then this is my final slide, which basically gives you what is the insight into that work, which is that you can control the geometry, say the height or the width of these channels, here represented by the standard deviation of this Gaussian profile. And by controlling both levers, you can, of course, tune your local resistance from, let's say, a low value to high value. And you can also tune your non-local resistance from a high value to a low value, which were the two opposite trends we observed. But now when you match the scaling of one into the other, you realize that operating at this length scale, where the inhomogeneity is below the characteristic length for a spin transport, and the thickness is below the characteristic length for charge transport, now gives you this possibility that the two transport regimes scale differently. And now you can try to take one of these maps, add it here, and see what happens if you walk along that contour, which then leads you as a result that you can fully tune, say, the charge-based resistance while keeping the spin non-local resistance constant, and vice versa. You can take one contour from here and map it here, and now modulate fully the non-local spin resistance while keeping the charge-based resistance fixed. And this is something that in these very easy systems, which are metallic systems, is not possible to do if you operate in the homogeneous thin film regime. You need to introduce curvature or some sort of small scale inhomogeneity in order to achieve this independent control of the two transport regimes. So to me, this was really a revelation, and I'm very conscious of the time. So I just leave you with these take-home messages that the 4 scales we cover really matter. Some of them are very easy to achieve in exotic materials. Others we can actually exploit even on materials that we have long forgotten, but that certainly will be the first one to be applied technologically, and therefore there is a work in working on those. And I happy to take your questions after just recognizing all the amazing collaborators, in particular the student, Kumar Das, that work on this course transport work, and the rest of the team, of which I have made some advertisements for the students in Manchester, and you're very welcome to check their talks and posters. And thank you all for your attention.
Thank you very much, Ivan, for the very nice talk. I think we have time only for a couple of quick questions. So either post on the chat addressed to everyone, or simply unmute yourself and then speak up.
I have a question.
Yeah, please, Andreas.
So if I understand this correctly, this is not an intrinsic, I mean, you don't tune the metallic system as such. I mean, you would get the same result if you have a thin layer of aluminium and a thick layer of aluminium, and you tweak these two thicknesses, right?
Absolutely. So this is where the mismatch between the theory and the experiment lies.
But you don't need curvature as such, right? It's just a...
No, you don't need per se the curvature if you can make the device on paper. Thanks. But how do you make the device in practice? That's where probably the only viable way is to use the curvature or the geometry as an aid to achieve that corresponding architecture. Yeah.
Thanks.
I just said that on the chat there was basically the same question, was if the same effect of the trench would be achieved in a flat channel, just modulating the width of the channel inhomogeneously.
Well,
I think that
in principle, yes, but then again, is how do you make that in practice? Because then you would really have to go for a channel that is so narrow that you are hitting this regime of, you know, few tens of nanometers, which is in principle fine to do with a state-of-the-art electron beam lithography, for example, but it's, you know, really hard to do in a well-controlled way. Whereas here, it's much easier just to control the amount of material you deposit, do it all at once, and let the geometry of the substrate do the job for you. That's it.
Yeah, all right. I think we have to move on in view of the time. So thanks again, Ivan, for the very nice talk.
My pleasure. Thank you very much for the opportunity.
And we move on. The next speaker, I think we stay in Basel, and is Andreas Baumgartner. Title of his talk is a quantum dot spin valve. Yeah, now I hear you, but we lost the slide.
I could not go to unmute with this is shared when this is shared.
With the share, yeah.
Oh, here we go.
Yeah, perfect. Thank you very much. Please.
Let me go to laser pointer. So yeah, so thank you for having me in this session. So I give you directly the outline. So the goal is often in these topics that we want to extract spin information from charge currents. There are basically in this talk, there are 2 steps only. So it's a simple one. So I want to show you that a single quantum dot can act as a spin filter. That's at zero magnetic field. That's what I want to show you. And to prove this, I will show you experiments in a double quantum dot spin valve. So first, I would like to thank Christian Schönberger, because this was all done in his group at the University of Basel, and the work in the lab was mostly done by Arnav Bortoloy, PhD student in our group, and we obtained excellent indium arsenide nanowires from the PISA group of Lucia Sorba. And so now let's start with the presentation for good. So it's maybe a bit basic for this session, but so the goal is we want to measure electrical charge currents, because that's the standard thing to do, but we want to find out information about the spin degree of freedom in some system. So what we would write down to start with is ideal projection operator. So you project onto spin up or spin down with respect to some quantization axes. So now in the lab, we don't have perfect protection. So if you take a ferromagnet, for example, and you shoot in some spins, they either go to spin up or spin down density of states. And this is usually described by polarization, where the density of states up minus the density of states down gives you the spin polarization. And then when you calculate the current, then you get an effective projection operator. So that's basically the current. And then if you see that if you have large density of states up and the small one, then your current is dominated by the spin up current, and then you would actually find a spin up state. But there's also a false positive. So in Corona times, we can talk of false positives because we also have a density of states of the wrong spin species. And of course, when we flip the magnetization, we get the opposite thing. And we get the ideal measurement operator if we have full spin polarization. So if we want to combine two of these elements, so we want to do a spin transport experiment, then we have one ferromagnet, some insulator or some non-magnetic region, and then we go into a second ferromagnet. And so that's from this review here. So that's a 40-year-old idea that you have two spin channels up and down. And if you flip one magnetization here, then you get a reduced conductance of this system. So here is, so we saw that in the first talk this morning. So that's the simple, the basic measurement. You have a ferromagnet here, you have maybe a ferromagnet of a different width here, and then you apply a magnetic field from outside along this axis, and then you can go with the thinner one switches at a different external field, and then you can go from parallel ferromagnets to anti-parallel ferromagnets. So the switching we also looked at some time ago. So you can engineer these switching fields by the width of your magnet. So, but now we want, if you do the experiment, you tune the external magnetic field. So for example, on the red curve, here the spins are parallel down, for example, then they go anti-parallel, and if the external field is large enough, then they go parallel again. And then we can, if we work at zero field or in metallic structures, then we have a spin polarization. This is not tuned too much by magnetic fields or gate voltages or so. Then we can define this tunneling magnetoresistance. So that's basically the change of the conductance here divided by the sum of the two conductances. If you define TMR like this here, that's in the literature, there are different definitions around, but if you choose this one, then you get very simple expressions for the TMR, which basically scales with the polarization of these two ferromagnets. So now, if we want to do experiments like this, there's my personal wish list for spin filters. So we want, of course, a large polarization. So for typical ferromagnets, we have maybe 20 to 40%, but so that's really a bit small. If you want to go to larger values, you get you have to use difficult materials like Heusler alloys or chromium oxide, which is immediately changes into some other oxides that are antiferromagnetic. The second one is you want to access up and down magnetization individually. So you don't want to work at too high magnetic fields. And it should be compatible, the whole thing should be compatible with interesting device structures and materials. So we often work with semiconducting nanowires with a strong spin-orbit interaction. So there you could have some spin textures, which we recently reported. But it's also interesting to have superconducting elements nearby. So one topic that we used to work on a lot is Cooper pair splitters, where you have the spin singlet of a Cooper pair, you separate the two spins. One is spin up, one is spin down in the end. This has been done with ferromagnets some 16 years ago already in metallic structures. But one could also look at Majorana bound states. For example, there's a prediction that you should get some equal spin Andreev reflection if you have ferromagnetic contact. And there are many other devices, as we saw in Jelena's talk. There's a lot of things like spin Hall effect, and one could also think of spin qubits. But in the lab, we often have a problem because it's very difficult to fabricate ferromagnetic contacts. So the very first step is often the hardest. So we have to do ex situ fabrication. So you have residues in between from the fabrication and things like this. The interface should be atomically clean because spin relaxation can happen very fast. But there are also fundamental problems like antiferromagnetic surface reconstructions of many of these materials. So what I want to propose here and show you experiments is that we use quantum dots as spin filters, and the idea is really super basic. So you take a quantum dot without ferromagnetic leads, so we have unpolarized contact here, and then we spin split them using the Zeeman effect. So we get a spin up resonance and a spin down resonance if you want. So that's possible with large global magnetic fields. That has also been shown some time ago, but this was done at 8 to 12 Tesla, so it's very hard to get a decent superconductor nearby. And the other negative thing with this idea is you basically polarize your electrons very strongly, and you can not access parallel magnetization states. You can only access parallel magnetization states. So what we want to do is we take a quantum dot, and then we put nanomagnets, if you want, nearby, and the stray field here at the position of the quantum dot can then be large enough to get a spin splitting. So this we investigated a bit some 4 years ago, and we showed that the magnetic field, so here is a magnetic force microscopy picture, so of two nanomagnets, so we call them split ferromagnetic gates, ferromagnetic split gates. So the magnetic field is really located between these two magnetic poles and decays fast outside. So you measure the charge current through the single dot to start with, and this single dot this has some magnetoresistance on its own. So we plot the conductance as a function of the external magnetic field, and if we start with a parabola without the ferromagnets nearby, it's a symmetric parabola, which is mirror symmetric around zero magnetic field, for example. But then if we add the stray fields, so if we come down on the curve like this here, the stray field points in one direction, and the outside magnetic field, which is the black one here, gets smaller and smaller. So the total field, which is the green one, gets smaller and smaller. And then when the nanomagnet switches its orientation, we jump onto a parabola that is shifted by the same amount, but on the other direction. And this gives us a change in the conductance where we jump onto this other parabola here. And then we get this magnetoresistance curve that shows this hysteresis once we move up on this parabola, and then we move up when we shift in the other direction. If we sweep in the other direction, we get this other parabola. And that's what you see in the experiment. So here is an indium arsenide nanowire with these ferromagnetic split gates. We sweep the external field and record the resonance as a function of gate voltage and field, and then we extract, for example, the amplitude of the resonance, the width of the resonance, or the position of the resonance. And here in the amplitude, you clearly see when we sweep up, we sit on one parabola, then we jump to the other one when the ferromagnet, this ferromagnetic gate here switches orientation. We also see some effects on the width and not so much on the position. Okay, so here in this example, we had a switching field of 35 millitesla and a stray field of 50 millitesla. That's not so much, but if you look at the different experiments, control experiment for what is to come, then we get a similar switching field, but we can get much larger stray fields if we go closer to the quantum dot. So the closer we get, the larger stray field we obtain. And here is similar curve as before, but here we have a control quantum dot that is some 600 nanometers away from the ferromagnets, and there we basically see no hysteresis anymore. So we estimate that the stray field at this position over here is smaller than 5 millitesla. In similar device we couldn't detect anything. So the message here is a bit, you can use a single quantum dot to investigate your stray field, but now we want to look at the spin transport, and for this we need two of these quantum dot ferromagnet elements. So that's the idea here. So we combine two spin polarized quantum dots, one here and one here. And then you see when, let's say they're polarized in the same direction, then the spin up, for example, has a large transmission and the spin down has a small transmission. You can also look at the energy diagram to get the same thing. And if they are the magnetizations are anti-parallel, then we can get a low transmission because the two spins are both scattered back somewhere. Okay, so let's look at the experiment. So here is the device. So we have an indium arsenide nanowire here with a central gate that can be used to form a tunnel barrier here. And we have a quantum dot on one side and a quantum dot on the other side. And here we have these ferromagnetic split gates with two different widths, so that we have different switching fields. And over here it's a schematic for the same thing. So if we tune this middle gate strong enough, then we can go into the weak coupled double dot regime, where we get these transport triangles. And we now look at different cross sections of, measured on these transport windows. So we look at one pair of triangles here. So we choose a cross section for a gate sweep. Here, this is this axis here, and then we sweep the magnetic field up and down. And you already see by eye, so here we have large conductance, here a smaller one, and here it's inverted. So if we extract the amplitude, the current amplitude of this here in the upsweep, so this curvature here, that's a magnetoresistance of the bare wire. But then when the first ferromagnet switches, then we get a strong change, and when it switches both in parallel again, we go back to the original curve shifted in some other direction. So we can determine the switching fields better than it looks like here, because we can do other experiments to extract them more precisely. But then what we want to do is we want to orient the magnetizations of the ferromagnets in parallel, or in parallel like this. That's the minus minus plus 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 minus minus plus like this here. And then we want to look at the sequence of these four magnetization states of the magnets. So and then measure the conductance as a function of the gate voltage. And what you see here, we start with very negative magnetic fields. Then we get a magnetoresistance, a conductance curve like this here, so the wider reddish one. And then if we go to a bit, so these curves are all measured at zero external field. So what we do is we sweep somewhere until one magnet switches its orientation, and then we move this back into zero external magnetic field. So that's the blue curve here. Then we go to a very positive field. Then we get the red curve when they're parallel, but in the other direction. And then we move back down, switch one, go back to zero. Then we have the anti-parallel opposite that we have here. And you see that especially the anti-parallel ones, they're on top of each other, and the parallel ones, they show a larger conductance. And since these measurements are at zero field, we can use the simple equation to determine from the tunneling magnetoresistance, we can extract or estimate the polarization, which is here something like 27%, which is better than many, but it's still a bit disappointing, right? So what we want to do now is we want to use the electrical gating and some small external magnetic field to optimize these numbers. And that's the next steps. So first we go to a different resonance. That's one electrical tuning. And then you immediately see that we have a much larger hysteresis here. And if you look at the amplitude here, you see a very large hysteresis. And if we then do the same experiment and do these gate voltage sweeps for these different parallel and anti-parallel states, we get a much larger difference here. And what we did here now is we applied a small magnetic field of 40 millitesla. This is still compatible with most superconductors. And what we get here is this red curve as a function of gate voltage. So we get something like between 25 and 50% tunneling magnetoresistance. But then we want to exploit more the gate tuning, and that's what we did here. So we did a map where we tune both quantum dots. So that's a gate axis for one dot, the gate axis for the other dot. And if we take this optimized cross-section here, then this gives us the blue curve for the tunneling magnetoresistance. And now we can reach 80 to 90% tunneling magnetoresistance. The problem is that at these finite magnetic fields, we cannot use this simple equation anymore to extract the polarization. So we make a very simple model, basically two split, semi-split quantum dot states. We calculate the current, and the only parameters that go in are two G factors. They're fairly similar. The two stray fields, which we determine from some other measurements, and some offsets between the one offset between the two resonances and the width of the resonances. And what you see, I mean, I have no time to discuss this, but all the black curve and this inset, these are, this model reproduces all the experiments, all the many different types of experiments with one set of parameters. And the important thing is that we get out a polarization at the maximum, we get a spin polarization of 80%. So that's a very good number, and with this one can do very nice experiments. And if we look what limits this number, we find that our quantum dot broadening is now similar to the Zeeman splitting, but in another paper we have shown that we can, if we use ground barriers, we can go to very low, very large lifetimes, very low broadening, and then we could in principle achieve 100% spin polarization. And we can also engineer the geometry of the split gates a lot more. So here is my summary. So we can use a quantum dot with a stray field of a ferromagnetic gate as a spin filter at zero magnetic field. And I've shown you proof of concept in a double quantum dot spin valve, which we can reproduce surprisingly well with a very simple model. And then we find that we can have up to 80% spin polarization, and if we think a bit, we can get 100% in principle. And the beauty of this is that this principle of spin polarizing localized states we can apply to basically any system that shows some Zeeman splitting. So what can we do with this in the future? So theoretical question is, what's the role of spin-orbit interaction for these experiments, and what's the back action onto the measured system if we implant this now into more complex systems? So we started to look now at Cooper pair splitting, where we see the first signs of spin anti-correlation. So if we have a singlet and separate them, one should be spin up, one should be spin down, but one can do a lot more investigating Majorana bound states, or one can construct entanglement witnessing experiments and belt tests for electrons. So in this paper, we provide a roadmap for this. And as Jelena said in the previous talk, one could use these alternating nanomagnets also to generate synthetic spin-orbit interactions, for example, in these nanowires. Thanks for your time.
Thank you very much. Thank you very much, Andreas. We have time just for quick questions. Either post on the chat as usual or just unmute yourself. Maybe I can start with
Carmen, there is one question in the chat. Andreas.
Oh yeah, so thanks, Diego. So there is a question is about the tunneling magnetoresistance. Your tunneling magnetoresistance expression assumes no spin relaxation between injection and detection.
Yes.
If I'm not mistaken, is there any evidence of that, like ferromagnetic separation dependence of the spin signal?
So yes, so the model assumes no spin relaxation, but I mean, we would probably not notice because I mean, we have a free parameter for the tunnel rates, and which we can determine separately, and then since it's, I mean, it's really a nice double dot. So I mean, to tunnel through a non-magnetic barrier, we would probably not expect too much spin relaxation. But in the model, this model is too simple to account for this. We would have to put this by hand, of course. And then the second question, I'm not sure I understand it. So,
if there is any evidence of this spin relaxation, I believe, like ferromagnetic separation.
I don't think so, but one could for sure look into this in more detail. But I would say one would have to model this more carefully then.
Okay, thank you very much, Andreas, for the very nice talk. I believe we have to move on. The next speaker is Raffaele Battilomo from Utrecht University, and he will give a talk on quantum rings, quantum spinol disks and rings, I believe.
Hello, can you hear me?
Yeah. Yes, Raffaele. I will just give you a heads up a couple of minutes before the time's up. So please.
Okay. Hello, everyone. So I would like to thank the organizers for having organized this conference in such challenging times. So today I'll be talking about how a quantum spinol in a disk geometry can effectively serve as a spin transistor. So this work was done in collaboration with Dr. Scopino and Professor Ortix, who's chairing today, and led to the following publication. So before talking about quantum spinol disks, however, I would like to briefly review a system which is similar but profoundly different also, which are semiconductor rings, which have already been mentioned, I believe, yesterday by Professor Nita. So as we know, the wave-like nature of quantum states allows for interference effects to be studied. As we see in the simple sketch, we have an incoming state which is split among two different paths, and upon being recombined, if the state picked up different phases among the two paths, we can observe interference effects. So the interference setup which we are interested in studying is looks pretty much like this. Now we have two leads, one which injects and the other one which detects a current. And in the middle, there's a quantum interferometer. So we have something which produces the interference. And we're interested in looking at how the outgoing current is modulated by this interference. And we also would like to tune this modulation by varying an external parameter. And in our specific case, this will be the Rashba spin-orbit coupling strap. Now, Rashba spin-orbit coupling is a relativistic effect which appears in some materials and which leads to spin momentum locking. So the electron spin and momentum degree of freedom are no longer independent. So this leads to breaking the spin degeneracy of the system if it's not already broken. And moreover, what happens is that the electronic spin tends to align to the Rashba field, which looks like this cross product between E and electronic momentum. Now, for example, here we can see in the sketch if we've got an electric field directed toward out of plane direction and an electron which is moving around in a circle in the plane, the electronic spin then tends to align to the radially with the Rashba field. Now, it's also interesting to use Rashba because to some extent this Rashba strength can be tuned by means of an external electric field. Now, in the case of semiconductor rings, we have a setup which looks pretty much like this. So the unpolarized current is injected on the left, and then the electrons get split in two arms of the ring. Each arm has two movers, so two states, two carriers. So two are clockwise, so two are anti-clockwise, counterclockwise, and they recombine if E equals pi. And what happens is that the outgoing current is then modulated. Now, rings are typically described by effective 1D Hamiltonians, like this one here, which we can see. We have a kinetic term, which is proportional to the revolution frequency of the electron, plus two other terms, which are proportional to the Rashba frequency, and which contain the radial and tangential Pauli matrices, as I think you can see here. Now, the energy dispersion are the usual spin-split Rashba bands, but what is very interesting is this adiabatic parameter, which is defined as the ratio between the Rashba frequency and the revolution frequency. Now, this adiabatic parameter actually plays a role in the transport properties of these rings because essentially it's telling us how much these the electronic spin is not aligned with respect to the Rashba field. Indeed, this kinetic term delta squared phi tends to tilt the spins out of the plane, and hence during transport, unless the Rashba is very strong, spins will not be completely aligned with the Rashba field. And this is reflected in the conductance modulation. Now, this formula here was derived, I believe, first time by Professor Frustaglia and Professor Nita, and the details are given in this Nature communication here. So we see there are two phases which contribute to the modulation, which both depend on the Rashba strength. One is a dynamic phase, which we typically also see in other interference experiments. And the other one is a geometric phase, which is called the Aronoff-Ananda phase, which is just a non-adiabatic generalization of the pi-Berry phase. And indeed, when the Rashba is strong enough to have adiabatic transport, this tends to the pi-Berry phase. So the main difference, what can be observed in this conductance modulation is that, as we see here, the bold blue line, compared to the yellow dashed line, which is the conductance one would see if the transport was adiabatic for each value of the Rashba strength. So we have essentially a pi shift compared to this other line, to this other curve. And moreover, the modulation is has quasi-periodic oscillations, so there's no defined period actually. So what we thought was, okay, but what happens if instead of semiconductor rings, which we described as effectively 1D, we get a quantum spinol disk? So it still should have 1D edge states on its edge. So can we think about it as being effectively a semiconductor ring? Is there still some interesting physics there? So what is a quantum spinol? It's a topological state of matter in which we have insulating bulk and conducting edge states. The system is time reversal symmetric, and hence what happens is that these edge states are helical. So we have counter-propagating spin up and spin down modes on the edges, as can be seen in this picture here. This is a state of matter which has been achieved actually in mercury telluride and cadmium telluride quantum wells for the first time. And quantum spinol insulators are described by an effective Hamiltonian, which is a minimal 4-band model called the Bernoulli-Guggenheim Hamiltonian, in which the basis states, these E1 and H1s, are just combinations of electron-like, light holes, and heavy hole semiconductor bands. The Hamiltonian takes a block diagonal form in the absence of Rashba coupling. Since we're interested in the disk geometry, these blocks in polar coordinates look like this. Now A, B, and delta 0 are model parameters. Delta 0 is the bulk mass. And the topological phase is achieved when B and delta 0 have the same sign in this case. And in this case, the edge states appear. So what happens is that we can use an ansatz to write the edge state wave function for these quantum spinol disks, which has the following form. Now I are modified Bessel functions. M is the eigenvalue of the angular momentum, which still commutes with the Hamiltonian. And it also has to be half integers. It's quantized because to ensure the periodic boundary condition and of the wave function. And C and these C1 and C2 are depend on the model parameters and the energy, but they're constants. So if we go and calculate these energy dispersions, we find, of course, these linearly dispersing states, which are time reversal one of each other, which also tend to become less linear when we go towards the bulk states. And what's more important is that they are exponentially localized at the boundary of the system, as we would expect. But what happens now when we add the Rashba coupling to the model is that we break inversion symmetry and we couple the E1 and H1 bands. So we can no longer describe the system as a, well, it has to be solved as a 4x4 Hamiltonian now. We cannot write it in a block diagonal way anymore, but we can still write the edge states in the following form. So once again, we can plot the dispersion relation of these states, which is once again linear around zero energy. But what's more interesting is that if we calculate the expectation value of the SX spin operator for these edge states, for example, for one of the two time reversal pairs, is that by increasing the Rashba coupling, this expectation value starts to increase. Hence, it's signaling that the Rashba field is starting to tilt the spins of these edge states toward the plane. And moreover, at the two opposite sides of the disk, so if phi equals 0 and phi equals pi, the two projections have opposite value. So now what we can do is actually, as was done with the semiconductor rings, we can effectively study a 1D affected Hamiltonian, since the edge states are localized on the edges, and the physics, when the energy is in the bulk gap, is entirely determined by the edge states. So what we can do is we can neglect the radial dependence and the orbital degrees of freedom of the wave function. However, the physics of the transport properties will still remain the same. And we can use an effective 1D Hamiltonian, which just describes S-like electrons on the disk boundary. So we use a Hamiltonian which looks very much like the one of the ring, except there's a key difference, which is this, the kinetic term is no longer there, but we have a linear term, which depends on sigma z now. And now we have this frequency omega z, which is essentially proportional to the Fermi velocity of these edge states. And we can once again define a parameter QR as the ratio between the two frequencies. Now, the main difference of these quantum spinol disks compared to the rings is that we now have only half of the carriers. So we will only have one clockwise mover and one counterclockwise movers, which will have to be one, the time reversal of the other. So one will be directed in one, the spin will be directed in one direction, and the other will have the spin directed in the opposite direction. This leads, however, to an unpolarized conductance, which passes through the ring, through the disk, which is not modulated in any way, shape, or form by the Rashba coupling. Well, this was somehow to be expected because it is a consequence of the topology. Since we have only one spin polarized carrier per edge, there is no interference between the two states when they recombine when leaving the disk. So, however, what we thought could be interesting to see was what happens when we inject a polarized current. So let's imagine of injecting an electron polarized along the x direction. When it traverses the disk and it comes out, is it still directed along the x direction, or has it rotated somehow due to the Rashba coupling, which we can tune inside the disk? So there are two key angles here again, once again, which is gamma, which is the tilt angle given by the Rashba, and theta, which is the angle, the in-plane angle, which the right lead has, the detector in the right lead has, let's say. And what we find is that the polarized conductance is instead has a modulation pattern, which looks pretty much like this. Now here in the density plot, we look at three cuts. Gamma equals 0, which is at 0 Rashba. So at 0 Rashba, of course, the injected spin, if it enters, let's say, in the x polarization, it comes out as an x polarization. So the conductance is maximum at theta equals 0 and 2 pi, and it's, of course, minimum when the detector is placed in the opposite direction than the injector. At gamma equals pi fourth, on the other hand, we have that the outgoing spin is completely out of plane. So all the projections on the plane are all the same, and we have indeed a constant conductance. And for sufficiently strong Rashbas, what we find is that, of course, the spin is flipped, and essentially it comes out completely reversed. So essentially what we can say is that by tuning the Rashba, we can turn on and off the outgoing current and essentially use it as a transistor, a spin transistor. So yeah, coming to my conclusions, we have seen, well, semiconductor rings are very interesting because, of course, they can be used to study the geometric phases of the electrons acquired by the electron when they traverse these rings, and of course, like the, I don't know, Phenom phase. And however, what happens is that for single rings, if there are some asymmetries, for example, between the two arms, the modulation pattern can be altered. And indeed, that's why I believe in the experience they have arrays of rings to kind of control these asymmetries effects. Well, on the other hand, quantum spin orbits do not serve as interferometers, but can be used as all electrical spin transistors. Edge states are protected by time reversal symmetry, so we have ballistic transport, and phase coherence is ensured. Moreover, deforming the edges of these systems does not really alter the topology, and neither does it alter the transport properties of the disks. Now, I'm not sure if I still have time. Okay.
I think your time is up.
Okay. So
if you want to use 1 extra minute.
Okay, I'll use 1 extra minute, since the title was actually also about, I had submitted also something about bending 3D topological insulators, because indeed here deformation of the geometry does not alter properties, but what we have done in a separate work was actually investigate what happens when we deform 3D topological insulators. Now, these are 3D materials which have non-trivial topology and host Dirac cones on the surfaces. So what we have seen is that by bending in a non-uniform ways these systems, we can tune the hybridization gap that we find between these two cones, and such a way to actually promote to change the topology of the system. We actually found out that above a certain critical bending, a certain critical strain, the system goes through a topological phase transition from a quantum spin hole insulator to a normal insulator. Actually, these energy shifts have also been observed in bismuth telluride nanowires. But what's even more interesting is that when these hybridization gaps are actually of the same order of magnitude of the bulk band gaps, we can actually have the opposite happen. So we can pass from a normal insulator to a quantum spinor and back to a normal insulator. So we can kind of, through this strain, have an oscillating behavior of these topological phase transitions. So this was just a flash, but if you have any questions regarding anything I mentioned, please feel free to ask them. Thank you very much.
Thank you very much, Raffaele, for the nice talk. We have a question by Mario. He asks, when you say that the deformation does alter the transport, do you also refer to changes of the Rashba spin orbit due to nanoscale curvature effect? Does not alter, sorry. When you say that deformation does not alter the transport, do you also refer to changes of the Rashba spin orbit due to the nanoscale curvature effects?
No, 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 no. Of course not. Now, when deforming the disk, I cannot be sure that the Rashba is deformed, changed. But I'm pretty sure that well, of course, the helical edge states will still be there. So there might be some microscopic details changing, but this is, of course, I mean, nothing is quantized here, so there is no like topology protecting the details of this modulation pattern. So I cannot exclude that the Rashba coupling might change. Yeah.
Yeah, some higher order correction to the version. Yeah, for instance. If there is no other question, now I will hold on a second because before I stall out a question to Andreas. I think there's not. So thank you very much, Raffaele, again.
Thank you.
And we move on. Next speaker is Mario Cuoco from the University of Salerno, Spin CNR to be precise. Hello, Mario. So his talk is about designing topological phases, spin texture, and spin interferometer by nanoscale shape deformation. Mario, I will also give you a heads up when time is almost up, and I will also give you an extra minute to be.
Can you hear me, or is it?
Yeah, yeah.
Okay, so good morning, everybody, and thanks to for this organizing this symposium. Although it's not extremely exciting to be everybody separate, but I think it's nice to hear all these signs. And okay, today I will talk about work we have been doing in the last 5 or 6 years. I mean, about using geometry to design spin textures and interferometry and also topological phases. So basically, the people who are been involved in this work is one is the people in Salerno, Paola Gentile, who you also listened yesterday. Zhujian Ying, he was in with us. I mean, now he's in Lanzhou in China, and then the group of Carmine Ortix in Utrecht, and also other people. I mean, in Salerno, Caio Ocean, and Victoria, they also joined the part of the project we have been working on. Okay, in this talk, I aim to present 2 main parts. I mean, which have been carried on. So about Rashba spin orbit coupling in electronic channels with a non-trivial geometry, and I will present you how the spin textures are obtained, what is the spin interference you can get, and transport when you have a genetic shape of these channels. And then I will, if time permits, I will also discuss how you can get topological states when you move to a periodically designed nanostructures with inversion symmetric breaking, with the Rashba spin orbit coupling. So I start with a very general slide saying that, okay, spin orbit coupling, inversion symmetric breaking is very general, it's very ubiquitous, and this is a really a key ingredient in many quantum platforms, in many quantum materials. And in this review paper, I think it's nicely mentioned. I mean, what you can do by having, I mean, by exploiting, I mean, this the spin-orbit coupling and designing materials like spinol or topological insulators or Majorana fermions. We heard about it, and also by controlling, I mean, spin orbital part of for quantum technologies and also in 2D materials and so on and so forth. So here in this talk, I take a little bit different perspective, and we started to ask the question. I mean, if you have an electronic channel like this object on a surface, and yet there is a inversion symmetry breaking because due to the breaking inversion, and you ask, okay, how you model these with a generic shape, and it turns out that you write down your Hamiltonian, and basically you instead of having a Rashba field which is uniform, I mean, you have a Rashba field which can change direction because now the momentum is changing, I mean, along the trajectory, and then you have to introduce, I mean, the curvature, I mean, of your channel, and this will render explicitly in Hamiltonian, and there is also a quantum geometric potential, which it's a pure quantum effects you obtain when you confine your electrons on a curved, I mean, nano profile. And so the first question I would like to touch then, okay, we know that if you have a straight channel, your electrons, they will move and your spin will be locked to the propagating mode, and along, for example, if it's along y and the momentum is along y, your spin will be along x. So the question is, what happens if you have so what happens to the spin when your electron is propagating along a channel which is a generic shape? So then you have to introduce just a little bit of mathematics, introduce a normal and tangential component to your trajectory, your curvilinear trajectory, and basically you can just parameterize that with curvilinear coordinate s. And you can introduce this angle Fs, which is telling you how the normal and tangential component are oriented. I mean, and then your spin will also, you can introduce the spin component by just having a Pauli matrices respect to this orientation. And the normal and tangential component, they are linked each other to the curvature. So the curvature, how strong is the velocity of changing direction of your electron is entering in this constituent equation, the Frenet equation, which links the rapidity of change of the normal and the tangential component. So now you ask what will be the spin, how it will do the spin. So you can solve this problem with is a quantum mechanical problem by putting yourself in the reference frame where the electron is when you sit on the electron, and basically you can derive an equation for the expectation value of your spin component with respect to an eigenstate of your problem, and you get a torque equation for the spin. So the variation in space of the spin is has a usual torque equation, but now apart from the spin from the Rashba coupling, this alpha r is the strength of the Rashba coupling. In unit is inverse length Rashba coupling. You see that it comes the curvature your trajectory. So what does it mean? And now, I mean, apart from the fact that your spin would like to be pinned along the would like to stay in the plane of the propagating direction, so your spin also gets an out of plane kick along sigma z in this torque equation. Which is proportional to the curvature. So what are the consequences of that? I mean, so the consequence of that, we can start by, so we can have, of course, I mean, an open channel, but you can also have a ring where the curvature is constant. And if the curvature is constant, you quickly understand that your spin gets out of plane, and you had, I mean, yesterday by Professor Nitt, I mean, about this variation and the consequence on the geometric phase and on the transport. So your spin gets out of plane and stays constantly out of plane. I mean, with a component which is proportional to the curvature or radius of your ring. But now, what happens if your radius is not constant? I mean, and it changes as like, for example, you squeeze a ring and you get an ellipse. Just as a very paradigmatic case, so basically you take a ring and now you make an ellipse, and and your curvature is very large at this point of the ellipse, and is very small, I mean, at the other part. So then your electron, which is moving in this elliptical shaped nano ring, I mean, it will feel more, I mean, more torquing out of plane at this point and less torquing at this point. So what is the consequence? Because it's a non-uniform now problem, and your electron has to adapt. I mean, it cannot keep a fixed direction in space, because your curvature is changing and then your electron has to adapt to this space-dependent torque, geometric torque. So then you can use this. You can take the block sphere and use a representation of the block sphere. I mean, so the spin in each point can be just one point on the block sphere, and sigma. And instead of using the x, y, and z, use n, t, and z. I mean, which is more convenient, because the normal tangential sigma z, they come as a natural component. I mean, to see how the spin of your electron moves along the trajectory. So if the squeeze is very small, I mean, the spin is mainly in the plane, basically, as you expect. I mean, and if you start to squeeze more, I mean, at the fixed spin-orbit coupling, so your electron now is starting to precess around the normal. So you get an out-of-plane component, and the electron is doing this wiggling. So now you can go ahead and you have more and more squeezing, and so the curvature becomes really strong perturbation to your problem. And then you get more and more, I mean, the larger, I mean, the precession around n, and even, I mean, at some point your spin can travel across the equator, and you get some winding also around the sigma z. So usually your spin is precessing along the normal, but it can also, I mean, at some point when the squeezing is really large and you get the huge curvature effects, you can even precess around z, which ends up in this nice texturing. So this is more or less what you will have if you change the spin-orbit coupling, or you scale the length and the spin-orbit coupling in increasing in this direction, and more and more, I mean, here with a strong squeezing. So you see that you get so when the curvature is dominating, spin is strongly out of plane, and then when you increase, I mean, it becomes more in plane. I mean, increase the strength of spin-orbit coupling, and if you do the same happens here when increase more and more, I mean, this product, I mean, of the length and the spin-orbit coupling. So we can have a phase diagram at the end. I mean, just to wrap up this first part. So the phase diagram is quite clean. I mean, if the system is not, you can separate two regions. One is the black region where the spin is not winding around the normal or the z direction, the out-of-plane direction, and there is another region which is in the color, where your spin is winding a lot. I mean, and is winding a number of times, which is here in the color map, and basically here is more like that your textures have a sort of topological behavior, meaning that you can assign a winding number for each spin texture, and this winding number is changing when you increase the spin-orbit coupling. Or you can also travel horizontally by fixing the spin-orbit coupling. You can change the shape, and you will go from a no winding to winding along this direction, right? And what is also interesting, that you get all these tongue of a region where not only the spin is winding around the normal component to your ring, but also around the sigma z component. So these there are some numbers. You can basically definitely access this region by using semiconducting nano rings and exploiting the gate tunability of the Rashba-spin-orbit coupling. So once you have this picture of the spin texture, you can ask what is the consequence of the transport, and then you have to look at the geometric dynamical phases. You employ what is this known scheme or approach, Arnold-Van approach. So to determine what is the phase electron acquires when it comes back after going around in a loop. And for our problem, so this analysis is quite rich, and we found a very interesting relation. I mean, you can determine the Aronoff-Van Anden phase, and this Aronoff-Van Anden phase you can express in an elegant way in terms of the spin of the characteristics of the spin textures. What does it mean? That you can express the Aronoff-Van Anden phase and the dynamical phase in terms of the spin component of your eigenstate out of plane, depending on the position, the curvature, and this winding, the winding of N and T component around, I mean, around the outer plane direction. So you see here, you can really recognize the pi. So when the curvature is when the radius is not contributing, you get this usual pi shift. I mean, of your spin, which is going around. I mean, of a 2 pi, and then you see here that there is you recognize here this cosine theta correction you get when the radius is constant here. But if the radius is not constant, there are interesting contributions coming from the winding. So and then you expect that your transport also will be affected by this contribution. And okay, you see here that if you make the contour map of cosine of the geometric phase, when you enter the region of this winding of the spin texture, you get strong, I mean, the variation of the phase ellipse of the geometric phase. I mean, in all the regions that we found before here, I showed you before in this phase diagram of Rashba respect to the squeezing ratio of the ellipse. So this is a geometric phase, but you can also look at the transport, and the transport is basically one can use this relation which links the transport, the conductance and zero bias conductance with respect to the total phase. And you can see here that again, you can have this electric control and the geometric control by squeezing your ring. And in principle, you can geometrically tune the conductance by moving from having basically no conductance to large conductance, for example, from blue to green. Or you can have this region where basically there is no change at all induced by the curvature. And the same here. I mean, of course, I mean, in the limit of the radius, you recover the known results which have been developed by many of you, and Professor Netta was mentioning in his talk. And what is interesting is that you can also get some interesting change of the conductance when you go, I mean, basically when you take a squeeze, I mean, a squeeze ellipse instead of taking a constant radius ring. So again, I mean, this is something which you can try in the lab, and some of the, I think also the recent achievement and the results of Professor Netta group is going in this direction. So tell me, how many minutes I have more? I mean, left?
You have 3 minutes actually.
Okay, so then I can flash on these topological states in when you have a periodic pattern. So you can of course take a structure which is periodically shaped, which means that you have a pattern which is regular. And again, you can employ the same, I mean, modeling that I was using for the ring, for the closed path. And okay, so So this, in principle, this type of, this can be lithographically designed, I mean, experimentally, or it can appear in this, when you try to do this wrinkling on thin films, when you do this selective etching, or you can do also this mesoscopic, I mean, with combining gating, top-bottom gating or lateral gating on a straight nanowire. And okay, to also, you can also use this moving dot approach, which has been also discussed, I mean, yesterday and presented. I mean, that you have this moving dot and use these acoustic waves to design, I mean, a periodically serpentine of Rajba spin orbit coupling. And this has been shown indeed that your spin, I mean, the spin of your electron can be modulated, as I was mentioning before. So here we did the same. I mean, we take this tight binding approach for simulating, I mean, an effective serpentine structure. And okay, this is a bit technical, but to give you some results, I mean, depending on the periodicity of these, you can get some, you have a, basically that your bands that get, they open a gap. And that this gap is basically topological. So you open the system and it becomes topological. And okay, I make it faster. I mean, there are some specific regions where these topological states are, so you can realize, I mean, more exotic, but special feelings. I mean, and you can get even zero energy states. I mean, at the edge, which are pinned by symmetry, by chiral symmetry. And if you look at the distribution of the gap, like you would do in a charge potential, which is periodic, you can end up in a distribution which is richer. And this is because, I mean, the spin orbit coupling is a non-abelian potential. And when you do this modulation, you are basically introducing an effective non-abelian potential, which is not uniform in space, and then you recover a sort of this modified butterfly, like is done in another context. And I think that we predict, I mean, a nice topological state in this periodic classification, which is in a C2 plus. We can add another spot, I mean, of quantum case where you can get this C2 topological state. So with that, I conclude. I mean, I didn't have the time to mention that you can also have a very interesting generation of topological quantum pumping by applying magnetic field on this electronic shape. I mean, this periodic shape serpentine. If somebody is interested, I can answer in the chat. And okay, so thanks a lot for your attention.
Thank you very much, Mario, for the very nice talk. We have time for a quick question.
Stop sharing.
Yeah. From the chat, maybe, or just unmute yourself.
Sure.
No, you can unmute, Mario. I meant the possible.
No, I know. I was.
Maybe I can ask a question.
Sure, please, Andreas.
So if I have a simple 2D material and I look at all these trajectories, I have lots of deformed trajectories and so on. Do you expect that one could see something without fancy structuring? Does something survive if I average over many trajectories? Like in this, let's say, weak localization or something like this with something.
Okay, so now you mean whether the disorder will kill everything, or because of course
if you add in spin to weak localization, you get weak anti-localization with the right type of scattering.
Okay.
So can you think of that this somehow does something fancy to weak anti-localization, for example?
Yeah, in principle it could. I mean, but okay, but then you're so yeah. I think in principle it could give some fancy contribution if you have if you engineer in the shaping in a way that you allow the self-interference pattern to be only some of these, yeah, probably this is a good point. Maybe one should think a bit more and try to design something which will appear explicitly in magnetotransport, right? Yeah.
Something that survives everything.
Yeah, that survive. Yeah, sure. Yeah. So it's actually I have to mention that this analysis is without the magnetic field, without applying magnetic field. So it's zero field. But if you apply a weak field, if you don't start to mix up all the states, I mean, then yeah, probably something could survive. Yes, it's a good point. Thanks. Yeah.
Thanks.
Can I make a small comment, please, Mario, regarding
yes, sure.
Andrea's question? So it's yesterday in Nita's talk, he showed arrays of rings. They are not ellipses, but they are rings which have little deformations, of course, and certainly weak anti-localization signals were present. Hello?
Yeah,
I think Andreas, it's muted. But yeah, exactly. So you with those arrays, you would probably get exactly a response.
Yeah, but the problem Andreas is referring whether you can use the geometry to modify this contribution, the weak anti-localization.
Yeah.
So if I understand his question, I think he thinks that so this weak anti-localization contribution should be affected if something remains of this texturing, right, in the interference, right? Then you.
Yeah, what I meant is that certainly the curvatures are present in Nita's experiment, and there are fluctuations on the curvatures, and of course they're not ellipses. They're not there's a well-defined geometry which are rings, but with fluctuations of curvature, of course. So
okay.
Anyway, even if fluctuations of curvature are present, the main features survive, and certainly weak anti-localization is present. That's all what I want to say.
Okay, I understand. Okay.
All right, very good. Sorry to interrupt the discussion, but we acquired already a bit of delay, so I have to thank again Mario for the talk, and we move on. The next speaker is Marta Galbiatti from CNRS, I believe. Yeah, Spain also, Valencia, and she will talk about spin valves with exfoliated TMDs. So Marta, please just unmute yourself first.
Sorry. Okay, can you see my screen?
The screen is going, also the full screen. Yeah, please.
Okay, so hello, my name is Marta Galbiatti. Actually, I'm working now in the Instituto de Ciencia Molecular in the University of Valencia. And today I would like to present you some of our results about spin valves with exfoliated 2D materials, and in particular, molybdenum sulfide. I think I can put the list. Okay. So this was a collaboration between the University of Valencia and the Unité Mixte de Physique Lattice in Paris. So, well, not necessary here to remember you what spintronic is, just to remember here is a schematic of a basic spintronic device, is a magnetic tunnel junction, and this formed by a non-magnetic spacer sandwiched between two ferromagnetic electrodes. And these work as a spin polarizer and analyzer system. So when we have the system in a parallel configuration, we have a low resistance state. Then when it's in the anti-parallel configuration, we jump to a high resistance state. But now, why we want to use 2D materials for magnetic tunnel junction? Well, here in these kind of devices, the tunnel barrier is really sensitive. So it must be well optimized and high quality, and also interfaces play a fundamental role in the performance of these devices. So 2D material, being intrinsically thin, allows us to fabricate atomically thin layers free of defects that are very promising to be used as tunnel barrier in this kind of devices. And actually, the possibility to use monolayer in these devices was already demonstrated, for example, with graphene or HBN, in, for example, in some of this work here. But also, as I was telling you, interfaces play a fundamental role in these devices. And again, to the materials, since they offer us a wide range of properties from insulator to superconductor, from diamagnetic to ferromagnetic, allows us very large range for tunability. So some interfaces effects were, for example, highlighted with graphene, where a magnetoresistance inversion was measured due to some spin filtering effect, or with HBN also hybridization effects of the HBN layer with the ferromagnetic electrodes were reported, where a spin polarization inversion or enhancement could be measured in these devices. But 2D material also offer new properties, as they have a very particular structure. For example, recently we highlighted some band filtering effect in tungsten disulfide magnetic tunnel junction, as tungsten disulfide change is a band structure from the monolayer, bilayer, and so on. And this also has effect over the spin valve devices. And also, we can think the possibility to combine the properties of these 2D material, using them a little bit as Lego building block, and towards the development or in the future of multifunctional devices. So really, we have plenty of possibility. And until now, the main results reported concern graphene, as it was the first 2D material to be explored, and it is metallic, then mainly HBN, as it is insulating. But there are still plenty other materials to be explored, as for example, the family of TMDC materials that present semiconductive behavior, and many different band gaps are available. So this is why we first decided to focus over molybdenum sulfide, as it is the prototypical TMDC material, and we want to introduce that into a magnetic tunnel junction. So the first interest towards molybdenum sulfide for magnetic tunnel junction came in 2014, when some ab initio transport calculation reported, predicted a magnetoresistance up to 300% into an iron molybdenum sulfide iron magnetic tunnel junction. So this was really exciting, and 1 year later, the first experimental results started to appear, and some other came afterwards. But even if these are very promising results, as you can see, the magnetoresistance signal is much lower than the one predicted theoretically. So, and this is because when we have to fabricate the device, we have to face with one main technological problem, that is ferromagnetic electrode oxidation during the fabrication process. In fact, with molybdenum sulfide and the most of our materials, we have to deal with mechanically exfoliated flakes or transfer flakes. And so really, we have to take care to this effort. Actually, here is a summary of most of the results until now with 2D magnetic tunnel junction. And as you can see, a lot of work was done with graphene, and a big improvement was done when graphene was directly grown by CVD over ferromagnetic electrodes. So we completely avoid the oxidation of the ferromagnetic interface. And the same thing with HBN, a big improvement was done when HBN was directly grown by CVD over the ferromagnetic electrode. The problem of CVD is that the process must be changed and optimized for each single material. So it's really difficult, and until now only graphene and HBN were directly grown over ferromagnetic electrodes. And so to explore other material, we have to deal with these mechanically exfoliated flakes or transfer flakes. And the problem is that, for example, here, what they did was to take the bottom electrode and quickly in air, they transfer the molybdenum sulfide flakes, but still the surface is oxidized, and this has dramatic effect over the spin polarization. So what we wanted to do was to develop an in situ fabrication process in order to be able to incorporate mechanically exfoliated flakes while maintaining high quality and not oxidized interfaces. And so once we are able to introduce one material as molybdenum sulfide, then it's quite easy to change from one material to the other, and so explore the potential for spintronics. So to do that, we need to work in inert atmosphere in order to avoid the oxidation of the electrodes. So first of all, we deposit the bottom electrode by sputtering, and here is permalloy. And the key point is that using a special transfer chamber, we directly transfer the sample from the sputtering chamber to a glow box. So we avoid the exposition to the air and the surface oxidation. So once we are in the glow box, we mechanically exfoliate molybdenum sulfide flakes over the substrate, and then again, using the transfer chamber, we directly transfer the sample in inert atmosphere from the glow box to a ultra-high vacuum evaporator. So again, we avoid the oxidation of the ferromagnetic electrode. And once we are in the evaporator, we deposit a thin alumina layer that allows to passivate the sample. And so from now on, we can expose it to the air without any problem of oxidation. So this allows to select the desired flakes, as the alumina layer is very thin and transparent. And we proceed with the lithography process. So over the selected flakes, we open a hole of about 1.1 square micrometers. And just inside the junction, we remove by chemical etching the alumina layer. So we are able to take a direct contact over the flake. And finally, we complete the device with the evaporation of the top cobalt electrodes. So this is the schematic of our final device that we then bond into a chip and we measure into a cryostat. So let's see now the transport results. So here is a schematic of our device. It's a permalloy molybdenum sulfide cobalt junction. Molybdenum sulfide is multi-layer. And in this device, we could measure at low resistance and low bias, at a low temperature, sorry, a high magnetic resistance signal up to 5%. That is actually the highest value reported now in the literature with molybdenum sulfide-based magnetic tunnel junction. And this proves that with our fabrication process, we are able to maintain high quality and not oxidized interfaces, because otherwise these results should be 1 order of magnitude lower. But the most interesting point here is probably to note that the measured magnetic resistance, so the 5%, is much lower than the real magnetic resistance that we could potentially measure in our device. So to understand this a little bit better, what we did was to study the transport on molybdenum sulfide at a local level using a conductive tip IFM. So we mechanically exfoliate the molybdenum sulfide flakes over a cobalt alumina surface. And with the conductive IFM tip, we do a resistance mapping of the resistance of the flakes. So here you have the optical microscope image of a monolayer over the surface. Then this is the tapping IFM image. As you can see, we have a monolayer, we have a bilayer, and this is connected to a big bulk here. And here, this is the resistance map of molybdenum sulfide. So in order to be able to directly compare the resistance of the monolayer when it is insulated and connected to some other flakes, what we did with the IFM tip, we cut the monolayer into parts. And here we measure the resistance. And quite astonishing, what we observe is that when the monolayer is insulated from the rest of the flakes, the resistance is much higher than when it is connected to some bigger flakes. Actually, the difference is 3 orders of magnitude. So to prove this even more, what we did was now to isolate even this part of the flakes from the big bulk here and measure again. And what we observe is that now resistance is much higher. So what does it mean? It means that we cannot think about the transport from molybdenum disulfide as just vertical transport through the monolayer, but even in the monolayer, we have to take into account that there is a strong lateral transport contribution, and the charge are delocalized over the wall all the connected flakes. So this is why here the resistance was much lower, as the surface was much bigger, as we have the big bulk here. And this actually has dramatic effects over our magnetic tunnel junction. Here is a schematic of a typical magnetic tunnel junction. And the problem is that now we cannot just consider it as we can naively do a vertical transport through the middle of the junction, but we have to take into account that the current is not just vertically tunneling here, but it is delocalized over the wall flake. And the problem is that this means that only this part of the current maintains its spin polarization, while all this current that contributes to the transport loses its spin polarization. And this actually is exactly the same that we have in our device, because we have our small top cobalt electrode, and then the flake is much bigger. And the problem is that when we inject the current from the cobalt, we don't have just vertical transport here, but the current is delocalized over the wall flake. And as you can see here from the optical image, the surface of the flake is much bigger than the surface of the contact. So we can roughly estimate that the measured magnetic resistance, the 5%, is just a fraction of the real magnetic resistance that we could measure into this device if we didn't have this depolarization problem. Actually, this is not exactly true, because we need to take into account the spin diffusion length into molybdenum sulfide, but this was reported to be just in the order of some hundreds of nanometers. So even like this, if we calculate the spin polarized surface, is much smaller than the total surface of the flakes. So still we have a lot of current that contributes to the transport, but it loses the spin polarization. So again, roughly we can estimate that the magnetic resistance that we measure that take into account the wall current, the spin polarized and the spin unpolarized one, is about 19 times smaller than the real magnetic resistance that we could measure if all this current maintains its spin polarization. So roughly, we could have potentially a magnetic resistance up to 94% in this device if we didn't have this effect. And we think this is very important beyond the optimization on the interfaces, that for sure is extremely important, but this effect was quite overlooked until now in the literature, and we believe it is necessary to take into account in the future to be able to optimize and improve the performance of this kind of devices. So this just brings to my conclusion. Here, just to summarize, I show you an in situ fabrication process that allows to fabricate vertical devices with mechanically exfoliated molybdenum sulfide, maintaining high quality and not oxidizing interface. And this is very interesting, since now on we can change from one mechanically exfoliated material to another, and it's promising to explore the properties for Spintronics. And with this process, we could fabricate devices where we could see a magnetic resistance up to 5% in molybdenum sulfide-based magnetic tunnel junction. That is the highest value reported until now in the literature in this kind of devices. But the most important thing here is that we highlighted the fundamental role of the charge delocalization on the connected flakes, and we think this is fundamental, as the real magnetic resistance we could measure in this device could be up to 94% if we didn't have this effect and if we could avoid this effect. So thank you very much for your attention.
Thank you very much, Marta, for the very interesting talk. We have time for one, maybe two questions. There is a question by Francesco. He asked how much thick was the TMD flake, and how did you check that the transport was actually tunneling?
Actually, the transport is not tunneling in this case, because the thickness of the flake was about 6 nanometers. So we don't believe we are tunneling. And so this is why also we have this strong lateral transport contribution. But we demonstrated with CTIFM measurement that even in a monolayer, we still need to take into account this effect. But for sure, this was not tunneling.
Okay.
Okay.
Please, Andreas.
Can I ask a similar question? I also want to say that this is maybe not tunneling, and this immediately suggests that you can gate tune your barrier or your transport, at least in the MOS2.
Sorry, I didn't hear you.
Can you somehow gate tune? So if you change, for example, I mean, you don't have a gate, obviously, because you have electrodes.
Yeah.
But if you have a large flake and central electrodes, you can maybe gate tune the outside. For example, deplete it.
I don't know exactly if you want to make the geometry, because this is vertical. So
if you have a large backgate and you deplete everywhere the MOS2 except where you have the electrodes which screen the gate.
The method is over the wall surface.
Okay. And the bias dependence, you see a bias dependence?
We see a bias dependence, yeah. The magnetic resistance decreases with the increasing of bias as expected in a junction. But maybe, yeah, we could think about some different geometries.
Thanks.
We have one more question by Fernando. He asked if you tried etching away the flake area that is not directly under the top electrode.
Yeah.
Optimizing, yeah.
We didn't try yet. Actually, the problem is that it's not so easy to etch, because if you etch exactly the size of the top electrode, then you have some problems over the boundaries of the electrodes, and so you can have oxidation through that, and it's not really easy. So we are trying some different geometries and some different ways to improve this.
So I believe there is another question by Ivan. Ivan, if you want to unmute yourself, yes, please, Ivan.
Yes, thank you, Carmine. Thank you, Marta, for the nice presentation. Can I just ask a couple of items regarding this observation that the conductivity goes up in the single layer flake when you disconnect it from thicker layers, right?
Yeah.
Could it be actually an effect of the monolayer getting doped by charge transfer from the thicker layer areas? That's one comment. And the other comment is you are comparing the increasing conductivity going from monolayer to few layers, whereas the barriers in the devices, I believe they were not monolayers. So that also makes the comparison a bit not on the same ground. So can you comment on those two things, please?
Actually, well, the study of the monolayer was this. Well, we showed results over the monolayer, as it was the case where we most expected just a tunnel transport. But we performed the same type of experiment also with other thickness, and we see always the same behavior. So this is quite general. And so this is why we also apply that to our spin valve, because if we have it into a monolayer and then we try it with some different thicknesses, well, it's even more, even with thicker layers. And then I don't remember your second question, sorry.
That's fine, that's fine. My only comment remaining then would be that since you have access to the flakes for lateral transport, right? You could actually check if the assumption that the decrease MR is because of this lateral plus relaxation process before going into the other ferromagnet by comparing the values of the charge resistances you get for the vertical transport, which will give you an idea of how easy it is to go through, right? Versus a similar moly on ferromagnet but then looking at transport laterally through it. Because I believe that there should be a way to do a simple charge transport experiment that could give you an idea of what is the ratio between these two directions, and then check that the ratio you are getting of potentially higher polarization is a good figure. Just from charge transport, you can get an idea of if this ratio makes sense. That's what I meant.
Yeah, actually it was reported that there is the lateral transport contribution is much higher than the vertical one. But yeah, we didn't numerically did some experiment to measure it. But we focused over some previous results that were reported. Then they said that the ratios will be around 100% or something like this, if I remember well, in one previous publication from another group.
Thank you very much.
Okay, thank you very much again, Marta, for the very interesting talk. We have to move to the last talk of the session. Is given by Andrei Nikitchenko, and the title of the talk is Nanoscale Spin Injector Driven by Microwave Voltage. Please, Andrei.
Hi, everyone. Good day, ladies and gentlemen. First, I would like to thank the organizers for the opportunity to present my work here. I am honored to talk. Thank you. Now, the ongoing discussion is devoted to the theoretical study of nonlinear magnetization dynamics and spin transport. Namely, the work is entitled Nanoscale Spin Injector Driven by Microwave Voltage. And the presentation has the following structure. First, we describe the nonlinear magnetization dynamics in the free layer of magnetic tunnel junction. Then the derived results are employed to calculate spin injection and pumping into the gold or gallium arsenide over layers. And in the last part, the spin transport in a long semiconductor bar is studied analytically. Now we start from the description of the study structure. This is magnetic tunnel junction capped with gold or gallium arsenide over layers. The magnetic tunnel junction is comprised of two ferromagnetic contacts and a thin insulator magnesium oxide between them. The magnetization of the bottom thick electrode is fixed due to the strong magnetizing field, and the magnetization of the free layer top thinner electrode can persist when some external field is applied. This is due to so-called perpendicular anisotropy associated with the ferromagnetic insulator interface. To calculate the magnetization dynamics in this free layer, we solved the phenomenological magnetodynamics equation in the macrospin approximation. That is, we assumed the magnetization to be uniform in the whole free layer. Here, this effective field is the field acting on a free layer and is calculated as a partial derivative of magnetic free energy density, which includes bulk anisotropy, interfacial anisotropy, interlayer exchange coupling, and the magnetizing field. Now let's assume that the microwave voltage is applied to this structure. First, due to the spin-dependent screening at the interface, the microwave voltage is transferred into a microwave effective field, which acts on the free layer. Second, due to the finite tunneling conductance in the tunneling barrier, the microwave voltage induces electric current, which becomes spin polarized in the reference layer and exerts a spin transfer torque in the free layer. We calculate spin transfer torque via a well-known Slanchevsky-like term in the magnetodynamics equation. In the first part of our study, we solved the magnetodynamics equation numerically at different voltage amplitudes and frequencies. Namely, here in the slide, one can see three frequency characteristics of precession amplitude. In panel A, we can see small voltages, and here only one symmetric peak appears around the natural precession frequency. It's worth noting that the linearization of magnetodynamics equation gives us an analytical solution which matches the simulation results at small voltages. That's why the magnetodynamics expressed in the panel A is the linear magnetodynamics. At larger voltage amplitudes and panel B, a break near the resonant appears. It is hysteretic, that is, if we go forward, the break appears here, and if we go backward, the break takes place right here. Furthermore, at larger voltage amplitudes, a new break grows, and its frequency is 2 times smaller than the frequency of the main peak. At larger voltage amplitudes, more peaks and more breaks appear. We find that the nature of these secondary peaks is parametric resonances, and its origin is voltage-controlled magnetic anisotropy in the system. Also, this peak is very common for nonlinear systems such as Duffin oscillator and is called softening nonlinearity. We also confirm by our calculations that this nonlinearity is also due to voltage-controlled magnetic anisotropy. For example, if we substitute VCMA by microwave magnetic field, this break takes place from the right side of the resonance, and it is called hardening nonlinearity. And this result is confirmed by earlier experimental studies provided by other groups. Now, using this data, we can plot the precession amplitude at the main peak against the voltage amplitude. And here one can see 2 curves calculated for semiconductor capped and gold capped 3 layers. Note that the dependence is linear under some threshold value, and above threshold voltage amplitude, some nonlinearity appears with additional peaks and breaks. We find that gold capped 3 layer has larger spin mixing conductance. That's why its effective Gilbert damping is larger, and the magnetization dynamics in this case is weaker. To reveal the origin of secondary peaks, we plot the trajectories of the unit magnetization vector projected to the layers plane. The upper panels here correspond to secondary peaks, and the down panels correspond to some frequencies between these peaks. We mark by the blue color the voltage periods where the voltage is negative, and red color corresponds to positive voltage periods. One can see that negative voltage increases the effective field value, which increases the oscillation frequency, and the blue color corresponds to high frequency damping oscillation, whilst the positive voltage takes the magnetization far from the equilibrium. And the main point here is that at parametric resonances, the mean precession period is very close to the nature precession period at the main resonance. In the second part, we use this magnetization data to calculate the spin current entering gold or gallium arsenide over layer. For example, our 3 layer is capped by gold, and in this case, the spin current entering gold consists of 2 components. Indeed, the microwave voltage induces magnetization precession in the 3 layer, which is responsible for spin pumping entering gold and spin backflow. And due to the electric current passing through the magnetic tunnel junction, it becomes spin polarized in 3 layer and enters gold carrying spin. So there is also an electric spin injection carrying gold. And this spin current enters gold and decays from the interface due to the spin relaxation processes. Due to the spin orbit coupling in gold, specifically inverse spin Hall effect, this generates the transverse electric current, which induces a transverse voltage on the sample boundaries. That can be measured experimentally to estimate the efficiency of proposed spin injector. And we start from the plotting the temporal dependencies of all 3 components of spin current entering gold, which consists of spin pumping, spin injection, and is called total resultant spin current density. We propose to characterize the spin current density by its AC and DC components, and note that there is a significant phase shift between spin pumping and spin injection. So AC and DC components of resultant spin current are not necessarily equal to the sum of AC and DC components of spin injection and pumping. Also, an interesting feature is about the second component of spin current. Our numerical estimations show that the AC component of the resultant spin current is almost solely governed by spin pumping, whereas the DC component is almost equal to spin injection. And now we can plot an intriguing frequency dependencies of AC spin current entering gold. Here one can see all 3 components. And we find that the AC spin current entering gold in the secondary peaks is almost equal to the spin current in the main peaks. That means that if we apply the microwave voltage with low frequency, we can expect AC spin current, which is large enough, almost large as the main peak. Also, because of the out-of-plane precession, the third component of AC spin current is very large and varies with frequency negligibly. Also, we can calculate some interesting frequency dependencies of DC components. We can see that the DC components of spin current can change the sign at some frequencies. And the maximum spin current is not necessarily situated at the resonance frequency. For example, in the panel A, we can see that the maximum is from the right side of the break. And using this data, we calculated the AC and DC spin currents at the main peak entering gold as a function of voltage amplitudes. We can see that in linear regime, the AC component is linear and the DC component follows the square law. And here some non-linear regime with secondary peaks and breaks appears. Using this data together with finite elements method, we numerically solved the Laplace's equation to find the electric potential distribution in the metallic bilayer. And that gives us the dependence of transverse voltage generated at the sample boundaries as a function of distance from the interface. And we find that the normalized voltage is for DC spin current is larger than for AC one, because AC spin current suffers from backflow as opposed to the DC current. And the observed transverse voltage is about 10 nanovolts, which is high, sufficiently high for experimental detection. From the practical point of view, the spin injector based on semiconductors are of the great interest because the spin diffusion length is large and the spin relaxation time is large. So we can carry spin on a large distances. And we propose here to use a long semiconductor, specifically gallium arsenide bar, to carry spin far from the magnetic tunnel junction. Here, due to the conductance mismatch problem, the electric spin injection from the free layer into the semiconductor is suppressed. And only spin pumping is responsible for the non-equilibrium spin accumulation generation inside gallium arsenide. The top insulator is inserted to avoid spin leakage in a normal metal. The spin is pumped from the free layer into the semiconductor and diffuses to the left and right edges far from the free layer. And at any coordinate, it can be measured experimentally by a well-known non-local spin detection scheme, where the spin signal voltage is directly proportional to the spin density. First, we solved the one-dimensional diffusion equation analytically with the piecewise boundary conditions. And that allows us to plot the spatial temporal distribution of spin accumulation in a long semiconductor bar. Here, at this axis, these dashed lines correspond to the free layer boundaries, and the sinusoidal spin pumping is subjected to the gallium arsenide bar on a time period over two nanoseconds. First, we have to note that there is a large spin decay, spin signal delay in the gallium arsenide bar, which is provided by the large spin relaxation time and acts as a memory effect in semiconductor. Second, we compare short and long semiconductors bar. This bar is 2 micrometer, whereas this bar is 5 micrometer long. And the spin accumulation amplitude in these bars at any coordinate increases with voltage amplitude increasing. But there is a significant difference because in a short bar, there is no spin decay at sample boundaries, whereas at the same distance in a long bar, there is a large spin decay. And we attribute this effect to a small volume of short semiconductor bar, which saturates with spin, and spin has no area to escape in this case. That's why it accumulates in the bar almost uniformly. In the last part, we used the derived analytical solution to calculate the spin signal spectra in a gallium arsenide bar. Here one can see some bright lines which correspond to peaks at the frequency characteristics. For example, the brightest line is the main peak. We see that the excitation frequency matches the response frequency. But there are at least 3 more bright lines which demonstrate the fascinating ability to multiply the frequency via the structure. For example, the application of microwave voltage of frequency 0.7 gigahertz leads to the 1.4 gigahertz spin signal output. And the amplitude of the output spin signal is high enough for experimental detection. It's about hundreds of nanovolts. Furthermore, here the power consumption of the structure is plotted against the voltage amplitude, and we can see that it is extremely small. For example, this largest consumed power is more than 2 times of magnitude smaller than the consumed power by the spin injector driven by a microwave magnetic field conventionally. And in conclusion, we solved numerically the magnetization dynamics equation in the free layer of the magnetic tunnel junction. We find that voltage-controlled magnetic anisotropy in this system is responsible for softening nonlinearity and parametric peaks and breaks, Dolphin behavior. We calculated the spin current consisting of spin injection and spin pumping entering gold over layer, and estimated the transverse voltage generated by the inverse Hall effect to be sufficiently high for experimental detection. Then we solved analytically the spin accumulation distribution in a long semiconductor bar, and the derived spectra of this spin signal demonstrates the fascinating ability to multiply the frequency via injecting spin. Thank you for your attention.
Thank you very much, Andrei, for the very interesting talk. We have time just for one very quick question. Is there any question? Either post it or unmute yourself. In the meanwhile, I will make my very naive question. So you calculated the spin transport in gallium arsenide bar.
Yes.
Do you expect any qualitative difference in a semiconductor with larger spin orbit coupling, like indium arsenide, for instance?
I'm sorry, I did not hear you very well.
Yeah, so the question is if the spin transport characteristic would change if you would have a semiconductor with larger spin orbit coupling.
Yes. But we find from some experimental studies that the spin orbit coupling in degenerate gallium arsenide is very weak, for example, compared with gold over layer. And first, we tried to calculate the transverse voltage generated by the spin current flowing inside the gallium arsenide bar, but it was extremely weak. It was about picovolts. Because of very, very weak spin orbit coupling. That's why, namely, the spin signal, which is directly proportional to the spin accumulation, not the spin current. We used this non-local spin detection scheme.
Okay, I understand. Is there any other question? Yeah, Ivan, please.
Thank you for the talk. Quick question. Do you need an MTJ at the bottom? Because you inject from the microwave on the top gold or gallium arsenide, and you use the DC biasing, or let's say the bias between that top part and the bottom ground to inject from the bottom ferromagnet into the top ferromagnet, right?
Yes.
But that injection would happen if you have a tunnel barrier or if you have a GMR structure as well. So I just wonder, as you model this, if for very high frequency applications, a fully metallic structure might do as well.
Yes, thank you for your question. And indeed, we can apply microwave voltage to the static magnetization, so we can inject into the gold over layer. But in gold, we have a very small spin diffusion length, so we cannot carry spin for a large distance. And if we want to use semiconductor to carry spin very far, we have to use spin pumping. So we have to rotate the magnetization to induce magnetization dynamics. But the main point of this work is the frequency multiplication. So we...
Sorry to interrupt. It's just to clarify. I just referred to the bottom, to the tunnel barrier in the MTJ. At the bottom, the MTJ at the bottom, right? If you would replace that tunnel barrier by a normal metal, like for a giant magnetoresistive structure, wouldn't that injection process work the same there? That's the question. It's a simple question.
But why would I insert? Do you want to insert an insulating layer between the free layer and spin sink, gold or gallium arsenide?
Right. No, at the bottom. So between your two ferromagnets, the one out of plane and the one in plane.
Yes.
And you have your tunnel barrier.
Yes.
Right?
Yes.
If you would replace that structure with a GMR structure, so metal, ferro, metal, fully metal.
Giant magnetoresistance, to use giant instead tunneling magnetoresistance.
Yes, yes. And still keep the two anisotropies, everything the same. You just have a barrier that allows you more, you know, conductivity,
yes,
but more current. Would that work as well? That's the question.
I understand. And in this case, spin transfer torque would be almost the same, but in this case, we would not have the voltage controlled magnetic anisotropy.
Right, okay.
Because there would be no spin screening at the interface of an insulator.
Sure. Okay. Thank you very much.
There would be no frequency multiplication and nonlinear effects. Yes.
Right. Thank you. Thank you, Andrew.
Thank you.
Okay, thank you very much. I think we have to close the discussion and we have to also close the session. I would like to thank all the speakers of today and all of you that participated.
Wait, Carmine, we should check the picture probably.